Good afternoon, everyone. Uh, let's start. So in the previous class, we discussed fixed length and variable length compression and also lossy and lossless compression algorithms. So from this class onwards, we'll exclusively focus on lossless variable length compression. We'll see what the fundamental limits are and how do you design good algorithms to perform uh, variable length compression. Okay. So let's start with the example we saw in the last class. So in this particular example, the input sequence or the raw or the source sequence, it was basically a sequence of three binary digits, 3 bits, and associated with each sequence, there was a probability of occurrence of that particular sequence, right? So for example, 000 occurs with probability half, 001 occurs with probability 1/4, and so on. And for this particular source described by these probabilities, we assign code words, right, or compressed sequences. So the compressed sequence corresponding to 000 was just the bit 0, and similarly for 001 it was 10, and so on. And so therefore for 000 the length of the code word was 1. For this sequence, the length of the code word or the length of the compressed sequence was equal to 2, and so on. So as the probability of occurrence of that particular sequence increased, as the probability of occurrence of the sequence decreased. So as we go from top to bottom, the probability of occurrence of the sequence decreases, but the length of the sequence increased. Right? And that's kind of a common sense way of assigning code words to individual sequences or assigning compressed sequences to individual source sequences. That if some sequence is less likely to occur, then you can assign a longer code word. But if some sequence occurs very frequently, then ideally you should be assigning very short length code words to those particular sequences. All right, and we saw that for this particular code word assignment or this particular code, the expected length of the compressed sequence or the average length of the code was approximately equal to 1.984 bits. Right, so we're going down from 3 bits, which is the length of the source sequence, to an expected compressed length of 1.984 bits. But then there was a trade-off. So sequences which occur uh, which don't occur very often, so sequences with very low probability now get assigned very large code word lengths, right? And that's something that we'll have to live with, because it's impossible to have short code word lengths for all possible sequences. That is impossible if you want to recover the original sequence exactly. Right? So we'll abstract out the problem of variable length compression in the following manner. So we can draw a block diagram for the variable length compression problem. So you're given a symbol or whatever a sequence, the source file. This is the source, which is the raw file. And for each raw file, there is an assignment of a code word. All right, so we'll assume that the source is random, distributed according to px, and this px is known to us. And corresponding to each raw file, you have a compressed file, which is basically a binary sequence. And the goal is to ensure that we are able to recover the original file exactly given just the compressed sequence. Right? So the goal is to design this encoder and decoder such that x hat is equal to x all the time, but then the length of the compressed sequence could vary depend on x. For sequences which we know occur less often, the code word length could be small, but then for sequences which occur which have a very low probability of occurrence could be assigned a longer code word. All right. Any questions so far? All right. So as mentioned, we want to ensure that x hat equal to x all the time. So if we have such a code word assignment, if we have any assignment, then a basic property that we want our compression algorithm to satisfy is that it must be non-singular. So any compression algorithm or a code is said to be non-singular. So the compression algorithm, which I also refer to as a code, is non-singular if distinct symbols, if distinct source sequences or distinct source symbols are assigned distinct code word symbols. So if the following occurs, if x equal to x is not equal to x prime, then the encoded version of x is not equal to the encoded version of x prime. Right? And that's something basic that we want to ensure that the compression algorithm satisfies. Right? Because otherwise, if for two distinct symbols we have the same code words, then there is no way of recovering at least one of the original symbols. Right? So, and this happens for all x comma x prime. Right? So distinct symbols are assigned distinct code words. So obviously this is necessary if you want to ensure zero error. Right? Any questions? All right. So now suppose that our goal is to design optimal non-singular codes. Say I have symbols x1, x2, x3 up to x10. All right. So I have 10 symbols, and maybe the probability of occurrence of x1 is, let us say, half. The second one is maybe 1/3. The third symbol occurs with probability maybe 1/16, and so on. All right. Then what do you think is the so let's assume that I sort of write these symbols down in the decreasing order of probability. Okay. So as you go from top to bottom, the probability decreases. Of probability. So P of xi is always going to be greater than or equal to P of xi plus 1. Okay, so I just order these symbols down in decreasing order of probability. So in this particular example, this was already done, right? So this was in decreasing order of probability. Now, if I do this, then can maybe someone suggest a code word assignment? Right? How would you assign a code word for x1, x2, x3, and so on? Any suggestions? Right? We want to make sure that it is non-singular, so no two symbols are assigned the same code word, but it's a variable length assignment. So for different symbols, you could have different lengths, compressed lengths, but otherwise there's no other constraint. So how would you assign code words?
Maybe we can take x1 as its code word 1. And
So you assign the bit 1 to code
yeah,
for this, okay, and for x2,
x2 is 0, 1,
okay, 0, 1,
and then 0, 0, 1,
0, 0, 1, okay, and then so on.
and so on. Yeah.
Okay. Is there something better you can do? So, for example, you've used up 1 over here, right? But then you're never using the code word 0 anywhere, right? So I could assign this as 1. I could assign this 0, right, potentially. And for here, I could assign maybe 1, 1, right?
Yes, sir, but here we have to take in consideration that the high probability contains more information, and
Okay.
so we are giving a code word with most likely have ones. Or
Sure. I mean, but it doesn't really matter if I assign 1 to this or 0 to this, right? All that matters is the length, right?
oh, okay, sir.
Right. So, for example, what are the possible code words that I can assign, right? So possible code words could include just 0, 1, 0, 0, 1, 0, 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, and so on, right? So these are possible code words, right? And since these are in the decreasing, I'm ordering the symbols in decreasing order of probability. I somehow need to assign these code words to each of these symbols. Right? So these are all potential code words.
Sir, one doubt.
Yes.
So if you assign 1, 1 to x3, then how will you differentiate if it's 1 x3 or 2 x1? I mean,
Okay. So right now the assumption is that again we're looking at non-singular codes. So we're assuming that we're trying to encode just one symbol. Okay. We don't have two symbols. So we're never going to encounter two x3s or anything of that sort. Okay, we'll get back to your question in just a few minutes. But right now, my goal is to just design non-singular codes. So non-singular codes is one in which two symbols are not assigned the same code word. That's the only criteria that we need to satisfy. Is that clear?
yes, yes.
Okay. So therefore, now can you suggest how we would assign code words?
Then you can just go for like the highest probability will be 0, then second highest 1,
okay,
and then 0, 0, 0.
Okay.
Yeah, in that order.
0, 1, and so on, right? So that would be sort of the best thing to do. And you can't really improve over this, right? Because you're anyway assigning, you're using all possible code words you have at your disposal, and the small, and you're assigning them in the decreasing order of probability. So the largest probability symbol gets assigned the shortest code word, and so on. Right. So in some sense, this is the best that you can do. Right. So I won't get into the details of this, of how you analyze this, because I think we already did this in the information sciences and information theory course. But perhaps we'll quickly go over it. All right. So this is one assignment. It's a code. It's a non-singular code, wherein I'm assigning symbols to, code words to symbols. And for xi, right, the length of the code word corresponding to xi, right, is going to be something you can calculate it. In fact, I can play some more tricks. I can assign no code word, the empty code word, to the first symbol. I can assign 0 to the second symbol, 1 to the third symbol, 0, 0 to the fourth symbol, 0, 1 to the fifth symbol, and so on. So it's just to make it notationally convenient. And the reason why I do that is that if I use that particular assignment, then the length of the code word for the symbol with the ith largest probability. So this is the length of code word for the symbol with the ith largest probability turns out to be exactly equal to the so the first largest gets assigned a symbol of a code word of length 0. The second one gets assigned a code word of length 1. The third gets assigned a code word of length 1, and so on. So you can verify that the length of the code word for the symbol with the ith largest probability is just floor of log I to base 2. Okay, so this is a claim that I'm making, and this is something that you should check. The second claim that I'm going to make is that the probability of the ith largest symbol is always going to be greater than or equal to 1 over I. Okay, sorry, I'm sorry. Right. Mistake. It is always going to be less than or equal to 1 over I. All right. So for example, the first highest probability symbol, P of x1, obviously is going to be less than or equal to 1. P of x2 is going to be less than or equal to half. P of x3 is going to be less than or equal to 1/3, and so on. All right. Can someone tell me why this is the case?
So by contradiction, if we try to
Hello,
when
yeah.
we try proof by when we try some proof by contradiction. So for the very first one, when we see the probability is greater than or equal to 1 means
Yeah.
if that is equal to 1, then we don't have any other symbol. And if we take P of x2, if that is going to be greater than half, then the first one which has to be which should have greater probability than P of x2
Yep.
will not, we can't have.
Right, exactly. So if this is not the case, then even summation I, whatever j equal to 1 to I, P of xi. So this is obviously, so this is P of x1 plus P of x2 and so on up to P of xi. Now each of, since this is greater than, or if this is strictly larger than 1 over I, then obviously all of these should also be strictly larger than 1 over I, because this is the decreasing order of probability, right? So this would be strictly larger than 1 over I plus 1 over I plus 1 over I and so on, 1 over I. But there are I terms in this sum. So this would be strictly larger than 1. And that is impossible because these are probabilities and all of them can at most can sum to 1. So if you sum only the first I terms, it should sum to something less than or equal to 1. Okay, so given these observations, if we try to compute the expected length, if we try to compute the expected length, L of x, so this is summation over all possible x. So suppose that there are m symbols, then this is probability of xi times L of xi, and so this is L of xi, but L of xi is floor of log of I for this particular scheme, I equal to 1 to m, P of xi floor of log to base 2 of I. But we've just seen that P of xi is less than or equal to 1 over I, which implies that I is less than or equal to 1 over P of xi. So this is less than or equal to summation I going from 1 through m, P of xi floor of log 1 over P of xi, which is less than or equal to summation I going from 1 through m, P of xi log 1 over P of xi. Right? So the only thing the only observations we made were these two. One, that for this particular assignment, it's a non-singular code. For this optimal non-singular code, the length of the code word for the ith largest symbol, for the symbol with the ith largest probability, is the floor of log I to base 2. And the second observation that we made was that the probability of occurrence of the ith largest probability is always going to be 1 over I. So this holds for any probability mass function, right? There's no other assumption at all. All right, so for this, the expected length, we just calculated this, substituted it in, and then use these two observations here. So the expected length is going to be less than or equal to, in fact, it will be very close to this particular quantity. And this is a quantity which depends only on the probability mass function. So what is this equal to?
Entropy.
What is this expression?
Entropy.
Exactly. So it's equal to the entropy of x. So if you look at the optimal non-singular code, then it achieves an expected length which is less than or equal to entropy. In fact, it won't be very far away from the entropy. Right? So that's good, but have we sort of completely solved the problem? Not exactly, because let us see how we designed this code. So how would the encoder actually operate? It would have to sort of store this particular table, right? You would have to write down all the symbols in decreasing order of probability, and then use this maybe as a lookup table to find the corresponding code word. And the decoder would also do the same thing. You store a lookup table of all possible symbols, all possible code words, and then map it back. But then if you look at a larger sequence of symbols, then you would basically have to recalculate all of these probabilities once again, right? So as someone pointed out, in this case, you'll never be able to. So if the compressed sequence is, say, 0, 0, if the compressed sequence is 0, 0, one problem with this non-singular code is that unless you know the length of this particular sequence, you'll never be able to say if if this is x3 or it is, sorry, if this is, I guess this would be x3 would be 1, so x4 would be mapped to 0, 0. All right, so if whether this is x4 or this is x2, x2. Right, so that's a major problem with this particular code or this particular compressor. That if you have a concatenation of symbols, there is no reliable way of distinguishing between these two cases, and that is something that we want to avoid. All right, so therefore, what we're interested in is not just the code itself, but also what I call the extension of a code. Okay, so what do I mean by the extension of a code? So let us say that I have a sequence of symbols. I have a sequence of symbols x1, x2 up to xm. Right, this is my alphabet. So for example, think of this as maybe all the letters in the English alphabet. A, B, C up to Z. Okay, so this is my alphabet, and maybe I design a compression algorithm for encoding each of these symbols. All right. So if I do that, then I have 26 symbols in the English alphabet. So corresponding to this, I have 26 code words. Now, so that's good if I just want to compress a single letter. But then if I see a sequence of letters, say maybe APPLE, apple, then I would need to compress A and then P and then P and then L and then E. All right. So I need a way to go from a code book or a compression algorithm for single letters to multiple letters. A single letter code to a multi-letter code. And the simplest way to do it is just to concatenate. Right? So for example, let us assume that our alphabet consists of just 4 symbols, A, B, C, and D. So that is 0, 1, 0, 1, 1, 0, and 1, 1, 1. Okay, so the code for A, maybe let me. So the encoding for A is 0. The encoding of B is 1, 0, and so on. Now, how do we get the encoding of maybe a concatenation of these symbols? Maybe ADA. It is just the concatenation of the encoding of A, encoding of D, and encoding of A. This is encoding of A concatenated with encoding of D concatenated with encoding of A. In this particular example, what would it be?
Zero, 3 ones, 0.
Yeah, so it will be 0, 1, 1, 1, 0. So this is D, this is A, and this is A. Okay, so this particular mechanism, where if you have a sequence of symbols, then basically you encode it as a concatenation of the corresponding code words. So this is called the extension of a code. All right, so the extension is basically, so we already have an encoding function for single letters. Now we want an encoding function for multiple letters, and that is what the extension lets us do. So if I have x of 1, x of 2, up to x of n. If I have n symbols, maybe this is A, D, B, A, C, C, A, then the encoding of this is going to be the encoding of x of 1 concatenated with the encoding of x of 2 and so on up to x of n. Right? Or this would be the encoding of A, D, B, B, A, C, C, A would be the encoding of A, encoding of D, encoding of B, encoding of A, C, and A. Okay, so this is what I mean by the extension. Okay, so now let's go back, let's revisit the optimal non-singular code that we had, right? Or let's just take a smaller number of symbols. The optimal non-singular code, or maybe something slightly different. So I have A, B, C, and D. Let us say that I assign A the code word 0, B the code word 1, C code word 0, 0, and D code word say 0, 1. Okay. Now, what would happen to the extension? Now, AA would be assigned 0, 0. BB would be assigned 1, 1. AB would be assigned 0, 1, and so on. Right? So now the problem is that if there is no way of distinguishing between A, B, and D. Right? If the actual source file was just contained the letters A and B, then it would be encoded as 0, 1. If the actual file was just D, then also it would be encoded as 0, 1. So therefore the extension here is not the same. Right? So the extension is not non-singular, it is singular. So let me make it a little more precise. So what do I mean by the extension? So I already have an encoding map from the alphabet to whatever the set of binary sequences. So I'll use this special notation for any set A. For any set A star denotes all possible finite length sequences from A. So for example, 0, 1 star consists of all possible binary sequences of all possible lengths. So it could be the empty sequence, so which contains nothing at all. Maybe this is just a space, and then 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, 0, 0, 0, 0, 0, 1, and so on. All right. So the extension of a set, or what I denote A star, consists of all possible sequences of all possible lengths. Okay. And the extension of a code the encoder of the code is basically the set of all possible code words corresponding to all possible extensions. So it is the set of all encoding of xm or xm in, maybe let me not denote the length of the sequence. So all possible sequences x belongs to x star. Okay, so these are all possible code words in the extension. So it is, if we go back to our example, it is the encoding of A, encoding of B, C, and D, and also the encoding of AA, the encoding of AB, up to encoding of DD, and the encoding of AAA, and all of these. All right, so look at all possible sequences. So right now all we are given is the alphabet, right? So our alphabet is just A, B, C, D. Okay, and we want to design a single code for all possible sequences which come from this particular alphabet, right? All possible sequences consisting of A, B, C, and D of all possible lengths. Okay, we want to design a single compression algorithm, and the way the compression algorithm works is that it compresses A and concatenates it with the compression of the next symbol and concatenates with the compression of the next symbol, and so on. All right, and that is what I mean by the extension. So the extension is the set is the encoding of all possible finite length sequences coming from that particular alphabet. Is that clear? Are there any questions?
Sir, so when we are sending like this,
Yes.
what like how will the receiver know which is the maximum length code or something?
So it may not, right? So that's the point. So one maybe implicit assumption we will make is that, so let us say that you have a sequence, you have xn, some sequence of some arbitrary length. This is encoded to a code word of length k. So we'll 0, 1, 0, 0, 1, 1, 1, 1, 0, and so on. So one assumption that we could make is that there is some marker at the end which denotes end of the file. Okay, so that's one assumption we could potentially make. We'll see how we can even avoid this particular assumption. But for now, let us assume that there is some marker which I call the end of file marker, which denotes that the compressed sequence has ended. Okay. Sometimes what you do is that, like in implementation, you will know what the length of the compressed file is that is stored separately in some particular fashion. Okay, so our assumption is that when we're designing this compression algorithm, when we're trying to design compressors for extensions, we don't know a priori what the length of the raw sequence is, but we know what the length of the compressed sequence is, or we have some way of finding out whether we have reached the end of the compressed file or not.
Okay. So the receiver also should be aware of that table, no, sir? That
Which
encoder.
table? Exactly. So obviously it has to be aware of the table. Just give me a minute. End of compressed file. Exactly. So as you rightly pointed out, the encoder and the decoder, of course, have to know this particular table. But the advantage of this scheme is that now I don't need to construct a separate table for different source lengths, right? So even if the source sequence consists of 10 letters, I can use this table. If it consists of 100 letters, I can use the same table. I don't need to redesign a completely different table depending on the number of letters in the in the particular source, or in the particular raw file, right? So just a small table is enough. So if the length of the raw file is very large, then the size of this particular table is much smaller than the length of the actual than the length of the overall compressed file.
Okay, sir.
All right. So typically all of this information. So you don't really. The practical compressors don't store this as a table, but you would still need to be able to know how this mapping is done. And some information about this mapping is generally stored as a header in the compressed file. So typically the compressed file will consist of two parts: the actual compressed sequence plus some header information. So the header information would contain some extra information, maybe the length of or the value of k, length of ck. It could also contain information about what the actual distribution is, and maybe information about the encoding function. So how these are represented, these of course need to be represented in the most efficient form, but all of this extra information will typically be stored in the header. All right. So for now, what we are doing is that we are completely ignoring this part. So we won't worry about how we design the header. Our only goal is to design this particular mapping. So we want to make sure that this is as small as possible, and we'll assume that this is some additional overhead which we have to live with. All right. But what is important to note is that this, of course, so for example, if we assume that this is going to be stored in the header, then this makes our life easier, because this header is small if this header is small compared to the length of the file, that is compared to n, then this does not take too much space in comparison to the rest of the sequence, in comparison to ck.
So,
Yes.
sir, like won't the header information also be encoded with the same symbols, zeros and ones? So again, how do we distinguish?
Exactly. So typically what traditional compressors do is that there is a fixed number of bits allotted for header information. So maybe the first, I don't know, 64 bits or 128 bits will be dedicated for header information. So you have to incorporate everything: the length of ck, px, the encoder, whatever information in those many bits. And the rest of it is going to be the compressed file. That's one way to implement it, although it's not the only way to do it.
So it's not followed by every extension, the header. Because
No,
assuming we do not have a fixed length scheme, and
okay.
in order to distinguish between different different concatenations in in a single line, and we were trying to put some sort of information at the end of every extension. So in that case,
Okay.
I'm still not sure how it would work out.
So maybe I did this wrongly. So typically, as the header will always be in the beginning. Okay, so there'll be a fixed length header, fixed length header, followed by the code word ck, and depending on n, the actual length of the compressed sequence. So note that the header now depends on px, maybe it depends on the on how you design the encoder for single symbols. So the encoding of A, the encoding of B, of C and D. Maybe this is what the header contains as an example. And this will contain the compressed sequence corresponding to the extension of whatever the entire raw file is.
Okay, sir. Got it.
All right. So this is going to be fixed length, but then this, of course, will depend on the actual realization, but also depends on the length of the raw sequence. So if the raw sequence is longer, then this will be longer, but this will always be of the same size. Okay. Now there is a way to get around that as well, the fixed length, but for now we'll just assume that the header is fixed length and it contains all of this extra information that we require in order to decompress. It basically, one way of thinking about it is that this entire encoding table is stored in the header. It's a bad way to implement things, but it's still conceptually it is easy. All right, any questions? Okay. So now, so therefore, since we're using this mechanism of extensions to encode longer length sequences, the header can therefore remain fixed. But that at the same time, we have to design our code carefully because we want to avoid problems of this sort, right? So if the symbol was AB, we would not be able to distinguish it from D. Right, so this is to be strictly avoided, and therefore we come to the concept of a uniquely decodable code. A uniquely decodable code is a code or a compressor for which the extension is non-singular. So not just the code itself, not just the code for single letters, but also every extension should also be non-singular. So let's take the example. So 0, 1, 0, 0, 0, 1, A, B, C, and D. This is not uniquely decodable because the encoding of D is the same as the encoding of AB. All right, so therefore not uniquely decodable. All right, so it is uniquely decodable if you take any other x. So for all xn, for all x tilde m, we have the encoding of xn is not equal to the encoding of x tilde m for all n, for all m, for all possible sequences xn, and for all possible sequences x tilde m. Of course, given that xn is not equal to x tilde m. Right, so the two code words can be the same only if the raw sequences are also the same. Okay, so this is an example of a code which is not uniquely decodable. Now, what if you have the following code: A, B, C, D. A gets mapped to 0, B gets mapped to maybe 1, 0, C gets mapped to 1, 0, 0, and D gets mapped to 1, 0, 1. Okay, is this uniquely decodable?
No, sir.
It is not. Why?
Because C is equal to B. Like.
Okay, so the encoding of C, in this case, the encoding of C is equal to the encoding of BA. All right. Okay, so that's good. Now let's take a look at one more example. So you have A, B, C, and D. Let us say A gets mapped to 0, B gets mapped to 1, 0, C gets mapped to 1, 1, 0, and D gets mapped to 1, 1, 1. All right. Now, is this uniquely decodable?
Yes, sir.
It is, right? So no matter how many of these you concatenate, you'll notice that the code words are always going to be distinct for distinct sequences, no matter what the length of the sequences are. Okay, so this is an example of a code which is uniquely decodable. Okay, so that's good. So it's obviously desirable to have a uniquely decodable code, right? But we'll see that there's a certain problem with arbitrary uniquely decodable code. So right now we're sort of imposing more and more constraints on our compression algorithm. So of course we wanted singular codes because we didn't want any error at all. But then singular codes are not good if we want extensions. So we're now looking at uniquely decodable codes. And now we'll impose one more constraint and say that we don't just want it to be uniquely decodable, but we also want it to be what I call instantaneous or prefix free, or also sometimes called a prefix code. So a code is prefix free or instantaneous or prefix code if no code word is a prefix of the other. So it just follows from the name itself, prefix of another. Right? So you look at any two code words for single letters itself and find out if one of them is a prefix of the other. So let's go back to these examples. So take this particular example, and we'll also take a look at these examples over here. Right, so let's look at example number 1. Is this a prefix-free code? Is any code word a prefix of any other code word?
It's prefix free.
Sorry, can you repeat? I didn't hear what you said.
It's prefix free.
It is prefix-free, right? So by a prefix, I mean any sort of the first few symbols should not be the same as any other code word, right? So let's take this particular example, example number 2. Is this a prefix-free code?
No.
No, sir.
Why?
B is a prefix for C and D.
Correct. So So this is a prefix of this and this, right? So these two are basically the same. So a prefix of one code word is some other code word. So this is not prefix free. Not prefix free. What about this example? Is this a prefix free code?
Not prefix.
Why?
A is a prefix for C and D.
Correct. So this is a prefix for this. Right. So this is also not prefix free. Okay. So fine. So we looked at those. Now, is every prefix free code uniquely decodable? Is every prefix code uniquely decodable?
Yes,
Why?
because if we take any concatenation between two symbols, we won't get any symbol from the table we have.
Right. So what Nadine is saying is that if you take any concatenation of symbols, say x of 1, x of 2, up to x of n, it cannot be the same as some x tilde of 1, x tilde of 2, up to x tilde of m, because none of them is a prefix of anything else. So for example, let us take something simple. So let's say x of 1, x of 2 versus x tilde of 1, x tilde of 2, x tilde of 3. Right? So if the encodings of these two are the same, suppose that these two are the same. Okay, so then what can it mean? It must mean that, of course, the first few bits are the same. So either encoding of x of 1 is the same as the encoding of x tilde of 1, or the encoding of x of 1 is a prefix of the encoding of x tilde of 1, or the other way around. Encoding of x tilde of 1 should be a prefix of encoding of x of 1. Right? Is that clear? So if these two are the same, if the encoding of this is the same as the encoding of this, then of course they must agree on the first few bits. They must agree in all bits overall, which must mean that the first few bits are the same. And that means that either these two code words have the same length and are therefore have the same code words, or maybe one of them, maybe x of 1 has smaller length than x tilde of 1, in which case the encoding of x of 1 must be a prefix of encoding of x tilde of 1, or x of 1 could have a longer length than x tilde of 1, in which case x tilde of 1 should be a prefix of the encoding of x of 1. But clearly this is impossible because it's a prefix free code, and this can happen only if x of 1 is equal to x tilde of 1, because no two code words are the same, right? So if the two code words are the same, then it must be the same symbol itself. And you can argue in for each symbol one after the other in this particular fashion, right? So every prefix code is uniquely decodable. So therefore, if you look at the class of all possible codes, all possible variable length codes, so a subset of all possible variable length codes is the set of all non-singular codes. So all non-singular codes, and not all non-singular codes are uniquely decodable. All right, so within this we have uniquely decodable codes, but not all, as we'll see in the next class, not all uniquely decodable codes are prefix free. So this will be the set of all prefix codes. All right. So we'll focus on prefix free codes for a very specific reason, and we'll explore that reason in the next class. Okay. Any questions?
Sir?
Yes.
Sir, you took one example of uniquely decodable.
This no,
Okay,
not this.
the first one.
Yeah, it's the same thing. The first one, correct. Yeah.
Sir, I'm just asking, I don't know if it is correct or not.
Mhm.
But for B, in case I take some code as 101.
Okay, so you take this to be, so basically I have a new code which is 101. Okay.
So even now it is prefix free.
It is still prefix free, yes.
But it is not uniquely decodable.
Why is it not uniquely decodable? Can you come up with an example of two different strings which have the same encoding?
Sir, I just thought if we have a sequence 10110, so
You have, okay, let us take 10110.
0.
All right.
So
So one. Okay, so this is not a valid code word sequence at all, right?
okay, there is an okay.
All right, because 101 is a code word, but 10 in itself is not a code word. All right.
Okay.
So again, one assumption is that we always go from left to right. That's something to remember. And the assumption is that whatever sequence we have, there is no error. So there are no missing symbols or anything of that sort. So given a valid code word, we want to be able to decompress it correctly.
Okay. Okay.
All right. Okay, so let's stop at this point, and we'll continue in the next class.